couple of things I handed out to you guys. One is the solubility table. So you can bring this to the test. Okay, so bring to exam. All right, so do not memorize this solubility table. If anything, if you remember from Tuesday's lecture, what would I like for you to memorize? 4 words? Right, all nitrates are soluble. So we expect them to dissolve in water and be totally soluble. Okay, that's correct. So we'll use this on our exam, and we will use this to try to solve what are called double displacement reactions or precipitation reactions. Right. So we did one on Tuesday. Let's see. A lot of you said that, hey, this is white and it's a white liquid. And where is the solid? And you can see here. Okay, there's a solid right here that has sunk to the bottom. And this one, if you remember from Tuesday's class, I know we were leaving, this is barium sulfate. So it's barium sulfate, which is at the bottom. Is that soluble or insoluble? Insoluble. Okay, so if you want to take a look at it, pass it around. Okay, the bottom is the insoluble. We call that a precipitate. Okay, precipitate. Let's do one more. Yeah, that white thing is a precipitate. Let's do one more of these types of problems if you want. I know, David, you volunteered yesterday or Tuesday. Anybody else want to volunteer? We'll do one more. Anybody want to volunteer? We'll mix 2 chemicals together. That is chemistry again. You want to do it again?
Sure.
Okay. Wait, I'll give anyone else a chance. Anybody want to mix these 2 solutions together? Just go for it. All right, the 2 chemicals that we have now are lead to, I don't know if you guys can see this, lead nitrate. Okay, lead nitrate. All right, is this solid, liquid, or gas? Or aqueous?
Aqueous.
Okay. Aqueous. Okay, that means it is dissolved in water. Is it soluble in water? Okay, yes, all nitrates are soluble, so it is soluble in water. You can see this, okay? And we don't worry about the concentration, how concentrated it is, but for now it's 0.2 moles over liter. Okay, we're going to react this with 0.2 mole, or same concentration, and this is called sodium bromide. Okay? Is this solid, liquid, gas, or aqueous? Okay, it's dissolved in water. It's aqueous. Okay. All right. So we'll take. You can choose a test tube here. Okay. So David, I'll have you squirt a little bit of the blue cap bottle into a test tube, and then squirt a little bit of the yellow cap, which is sodium bromide. Okay. We're just going to mix them. You know. Yep, put it in. Thank you, ma'am. Hey, what did you do to my precipitate? Here, don't cross-contaminate. Okay. So, where did you... Don't be nervous. It's just like 30 people and your professor are watching you. If it was me, I'd knock everything down, but okay, looks like we got something here. All right, so yeah, okay, we have, just like in our previous mixing of those two solutions, we got a white cloudy substance. To me, this looks like a precipitate. It's just got to settle. Okay, you guys see it? Okay. Yeah, throw them away. All right, so we mixed two things that were colorless, aqueous, and we got something that's white and cloudy, and there's definitely a precipitate there. Okay, just let it settle. Okay, let it settle. All right, thank you, David. Yeah. So was there a reaction that occurred here? Okay, so a white, cloudy precipitate formed. Okay, the word is called precipitate. Have you heard this term before? Precipitate. All right, so what is lead 2 nitrate actually in water? Is this ionic or covalent? It's a metal with a nonmetal, so it's ionic. So what did we say in Tuesday's lecture an ionic compound will do in water, in aqueous? It does what? It dissociates into its component ions. Very good. Very nicely done, Gerardo. So what are the two ions that make up lead 2 nitrate? Okay, it's going to be Pb plus 2 plus NO3 minus. Okay, is this ionic or covalent? Okay, what two ions make up sodium bromide in water? Because remember, water will dissociate it into its individual ions. Okay, sodium ion and Br minus ion. So now a reaction will occur. Okay, we'll get a reaction. So this plus will react with this minus, but that's pointless because all it will do is give you this. Okay, this sodium will react with this negative bromide, but that's pointless because all it will do is give you this. But in these types of double displacement reactions, you want to do outer and inner. So inner and then outer. Okay, so Na plus reacting with NO3 minus, what will that give you? It will give you NaNO3, but what do we know about all nitrates?
Soluble.
Very good. So really, sodium nitrate in water is nothing more than sodium ion and nitrate ion. Okay, let's put that up here, NaNO3. Okay, I'm going to put aqueous here. So that was inner. What is the outer? Pb and Br. Okay, so that is going to be lead bromide, lead 2 bromide. Is that soluble or insoluble? Okay, now this is how I want you to do it on any test or exam. Okay, go up to your solubility table. Okay, what do we know about the bromides? This can be a little tricky, so you have to be careful. Okay, I'm going to read this out. Okay, all chlorides, bromides, we're interested in. All chlorides, bromides, and iodides are soluble. But a lot of people, including myself, will forget the except. Okay. Except which ones? Ag plus, which is silver, Pb plus, lead, and then this is Hg2, mercury. Okay. And then it says PbCl2, slightly soluble, blah, blah. Okay. So this is actually going to be PbBr2. Will it break down into its ions? Is it soluble or insoluble? Okay, so you have to worry about the exceptions, okay? So the exceptions are Pb plus and also Pb plus 2, though it doesn't tell you that. Okay, any type of lead. Okay.
PB plus is soluble or insoluble?
So the except would be insoluble.
Oh, insoluble.
Yeah, so here would be the exceptions. So would this be soluble or insoluble? Okay, if it's insoluble, what will the state be? Solid, liquid, gas, or aqueous?
Solid.
Solid, yeah, okay, solid. Very good.
I just woke up.
All right, so that is one answer on the exam. Okay. Okay, so this is called the molecular equation. Okay, so don't forget your states. Okay, we will not forget our states here. And you're right, Husong, this is solid. Okay, this is insoluble. So this is the molecular equation, and next we will do the net ionic equation. So the net ionic equation, we want to cancel out our ions that do not react. Okay, we'll cancel out the ions that do not react. And these are called spectator ions. So the spectator ions in this particular problem is sodium ion. It's there, but it's just dissolved in water. Okay, so the sodium ion cancels out with the sodium ion. Okay, what about the NO3 minus? Okay, the NO3 minus cancels out with the NO3 minus. So the ions that cancel out are called spectator ions because they're just there, okay? But they're not really producing the solid. So these are spectator ions. Okay, so canceling out the spectator ions, those that appear on the left and right, gives us another answer. So both answers I'd like for you to write on the exam. And that is the net ionic equation. Okay, so what's the net ionic equation for this one? Pb plus 2 aqueous, very good, plus
Plus Br minus PQ. PbBr2
Yeah.
solid.
solid. Okay, and we want to balance this. Okay, and we want to balance our molecular equation as well. Okay. Okay, so don't forget to balance. All right. So that is the identity of this white solid that you see here. Where's it? Okay. Oh, so you can see it. Okay. Oh, I know it's hard to see. Okay. That's a very beautiful looking precipitate. Looks like snowflakes. Okay. So at the bottom, we have a white precipitate. Okay, I don't know if you guys can see this, especially in the back, but I can pass it around. Okay, this is the precipitate. Okay, precipitate, and the thing that's at the bottom.
That will be PbBr2, right?
That will be PbBr2. That's exactly correct. And the liquid at the top, that's called supernatant. Okay, supernatant. Okay, so yes, Gerardo, the thing that settles at the bottom is called the precipitate. The supernatant is the liquid on top. What does the liquid on top contain?
The dissolved ions.
It will contain the dissolved ions. Okay, that is what it contains. It will contain the spectator ions. What else will it contain besides the spectator ions? H2O, water, which is the solvent. Very good. Nice job. It will contain water and your spectator ions. Okay, so this liquid on top contains your spectator ions. And your precipitate contains what? Your insoluble solid. In this particular example, it's lead bromide, lead 2 bromide. Okay, so we have the supernatant that's on top, the liquid, and then the precipitate, it's the solid that comes at the bottom.
What happens if, for example, instead of PB, we had an element that actually can dissolve?
Then it's no reaction. Okay, if this is aqueous and it breaks down into its ions, then it becomes no reaction. Okay, if you don't get a solid, you just put aqueous here, and then here is no reaction. Okay, it's a good question. Okay, if this is, it's not aqueous, but if according to the solubility table, if this was aqueous, you'd write aqueous, 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 but here it would be no reaction, NR. Okay, so our precipitate contains the solid that is insoluble. So this is an example of a double displacement reaction. Okay, so bring this to the exam so you'll know what is soluble and insoluble. Okay, we know all nitrates are soluble, but the other things, we don't want to memorize all of that. Okay. And also be careful about the except. Okay, except, okay, except, okay, so. And another thing I've noticed is you need to balance your equation. Okay, balance it. Okay, how many lead? 1. How many lead? 1. How many Br? 2, because I balanced it. How many Br? 2. What's the total charge on my reactant side? +2 minus 2 is 0. What's the total charge on my product side? 0. Okay, there's no charge here. Okay, there's no charge here. And this is -2, because you got 2 Br minus 2 plus 2. So it's mass balanced and charge balanced. In other words, always balance your equations. Like I said, this is mass balanced and charge balanced. So I'm going to write here charge balance and then mass balance. Okay. All right, let's do one more example here. Are we a little bit comfortable with this? Okay. Let's do one more on page 4 of our notes. Okay. And page 4 of our notes is this. Predict the precipitate formed by mixing Al, NO3 solution. So that means AlNO3 okay, aqueous with NaOH solution. This is called sodium hydroxide. Okay, so write the net ionic equation. Right. So as Gerardo said, if both of them are, if the products are both soluble, then it's no reaction. But let's see if we get a solid or a precipitate out of this. Some aluminum nitrate in solution is this, aqueous. Sodium hydroxide in solution is this, it's aqueous. What is aluminum nitrate in water? What ions will it decompose to? Aluminum ion, which is +3. Nitrate. Okay, this is called the nitrate ion. Okay, what will sodium ion in water dissolve into? Sodium ion, and what's the other ion? What's OH minus called? OH minus is called hydroxide. Remember hydroxide ion? Yes? All right, so we'll do outer and inner.
Do we have to balance it?
Sorry?
Do we need to balance it, right?
I like to balance it at the end.
Okay.
Yeah. But you do want to balance it. Okay, so we have NaNO3. What do we know about all nitrates? They're soluble, so really this is just NaNO3. That's goes into its ions. So I'm going to write that here as aqueous. And then what about outer? Okay, aluminum hydroxide. What do we know about aluminum hydroxide? Let's see here. Okay, let's go to our solubility table. Hydroxide OH minus. All hydroxide and phosphates are where am I? Oh, all hydroxides are insoluble except sodium, potassium. Hydroxides of barium and calcium are slightly soluble. So what are we actually looking at here? Aluminum. So would this be solid or aqueous? This would be solid. Very good. And the equation, the formula would be, if we do the switcheroo, Al, we switch it, solid, okay? Solid. So the up top here is the molecular equation. Now, will there be a net ionic equation to this one, or will it be no reaction? Okay, there will be a net ionic equation. How come? Because you produced a solid. What's the name of that solid? Aluminum hydroxide. What are the spectator ions here? Na and NO3. So now let's write our final answer, our net ionic equation, which is going to be Al plus 3 plus OH minus. You see AlOH3 solid. Don't forget the solid. And now, Gerardo, you make a good point. We want to balance this. Me, I like to balance at the end. If you want to balance it at the beginning, that's okay as well. 3. and this is called the net ionic equation here. So on the exam, you want a molecular equation, which is here, and then you want a net ionic equation. Okay, what will we not forget? Do not forget what? Balancing, correct, and what else? States. Do not forget the states. Okay, so these are common mistakes that I see in grading these tests and quizzes and so on. All right, so that is what we're going to call a double displacement reaction. And I want to give a couple of comments about acids. So acids also can ionize. So we have what are called strong acids. If you take Chem 2, which is actually going to be all, there's an entire chapter on acids and bases. So I don't want to get into so much detail unless you're taking Chemistry 2, where, they talk about this in so much detail. But strong acids give off H+, which I'm going to call a proton. Okay. So something like an HCl is a good source of proton, which is H+. Okay, these strong acids. H2SO4 is a good source of proton. Actually, this will give off 2 protons. What's another acid we learned in our nomenclature lab? Maybe nitric acid. Okay, so these ionize, and when they ionize, they give you, like I said, H+, and we will call H+ a proton. And then we also have, so we have strong acids, and then we also have weak acids. They give off H+, but not as much. Okay. Okay, not as much. Like I said, we'll talk about this in Gen Chem 2. And then on the other side of the ledger, we have our strong bases. Okay, while strong acids give off H+, strong bases take the H+ proton. Take, or they grab, or they abstract the H+. So this is also a good source of ions, and hydroxides are a very good base. So sodium hydroxide is a very good source of OH-. So strong acids, for an acid, I want you to associate with H+, and for a strong base, I want you to associate it with OH-. Okay. Strong base is anything that gives off OH-, and a strong acid is anything that gives off H+. Best example are the hydroxides. Alright, so that's all I want to get into that right now, because, like I said, you'll learn more about this in general chemistry the next course. Okay. Gen Chem 2.
So that's why when acid and bases react, you get water, right?
Right, that's called a neutralization reaction. Okay, it's a reaction between a strong acid and a strong base. By the way, all of these are aqueous, just so you know. In water, this is all happening in the solvent of water. All right, yes, as you mentioned, Husong, that a strong acid with a strong base, they neutralize each other. So if you react a strong acid is nothing but H plus with a spectator ion. Okay, a strong base is nothing more than OH minus with a spectator ion. So anything that's a strong acid is 100% source of H plus proton. Anything that's a strong base is 100% source of hydroxide ion OH minus. What happens when H plus and OH minus come together? Okay. They'll give us water, and this is a neutralization reaction. What is the state of water? Don't say aqueous. Okay, water is liquid, pure liquid. Okay, there's nothing inside that except water. Okay. Yes. Okay. So this is what we're going to call a neutralization reaction. A strong acid will neutralize a strong base. So this is all you really have to memorize, okay, for a neutralization reaction. So we did a double displacement reaction where you need to use the solubility table. This guy. We learned a little bit about acids and how they are a source of H plus, and bases how they are a source of OH minus. And I just want you guys to realize that if you take a strong acid and add to it equal amounts of strong base, you just get water. That is, the strong acid neutralizes the strong base neutralizes the strong acid. This is called a neutralization reaction. All right, so now let's do something a little different. Okay, we're going to clear our minds. Still remember this, don't forget this. And let's do something very different here. Let's talk about oxidation reduction reactions. Okay, these are called redox reactions. So what are the reactions we've talked about before? There's two of them. One is called the double, bless you. One is called double displacement. Okay, and the other one is neutralization. Okay, this is with the strong acid and strong base giving you water. Okay, so redox reactions involve literally the transfer of electrons. Okay, so redox reactions involve a redox couple. Okay, redox couple, which means someone gives an electron, and then what does the partner do? It receives or takes the electrons. That is correct. Okay, so that's the couple. So you give electrons, and a partner takes those electrons. Okay, that's the couple. Okay, so let's have a redox couple here. Husong, since you've been very active, so thank you. Let's be a redox couple, okay? Electron couple. So I'm going to, you're looking at me funny. So we're going to give electrons, and you'll take those electrons, okay? So I can give 1 electron, I can give 2 electrons, I can give 3 electrons. Okay, I'm going to give you 1 electron. Okay. Okay. Remember, this is the transfer of electrons, and electrons are E minus. Okay, E minus. So I'll give you just 1 electron.
Thank you.
All right. So I'm VJ. Okay. Okay. I'm going to give an electron away. Okay, and when I give that electron away, I become positively charged. Okay, positively charged. Okay, I am balanced. Okay, this minus and this plus balance each other out. Okay, so it's 0, 0 and 0 on both sides of the equation. Okay, you need someone to take an electron. In fact, these are really bad for your health. Free electrons floating around are really bad for your cells. There's a disease called ALS, amyotrophic lateral sclerosis, where the free electrons actually react with your membranes and the neurons, and you get paralysis. Okay, so these are really bad in a health standpoint. Okay, so for every giver, there's a taker. So Husong is going to take that electron. I'll put you in blue. Okay, so he takes that 1 electron, right? S-U-N-G. There you go. My apologies. Husong, okay? He takes that electron, and what will you become? Okay, negatively charged. Okay. So I give my electron away, and if I give my electron away, I become oxidized. Okay, I lose 1 electron. I lost 1 electron. Okay, Husong takes that electron, and he takes it, he receives it, he gains it, he becomes reduced. So this is an oxidation half reaction, and this is a reduction half reaction. Let's add them up to get the total reaction, or I'm going to call it the net reaction. Okay, so we'll do that. Okay, so this 1 electron that I give away, he takes it, so they cancel each other out. So what are we left with? We are left with VJ plus, you're blue, right? Yeah, blue. Goes to VJ plus this is our net reaction. Okay, this is our net oxidation reduction reaction. So all you got to do is replace this with actual chemicals, and you get a oxidation reduction reaction. Just replace it with actual chemicals. Okay, this is electron transfer. Another thing you want to think of for redox reactions is that these are electron transfers.
So in this case, they will need to be ionic compounds, right?
They don't have to be ionic. Okay, they don't have to be ionic. It can be covalent, but what we need to do is calculate the oxidation number to determine what gets oxidized and what gets reduced. Okay.
If they can form a bond or something, they just give out electrons. That's why it's not compound.
Right. Right. So in order to do this, we have to do what's called calculate the oxidation number. Okay. Okay, so that's all we're going to do. We will only calculate oxidation number. We will not do any balancing redox reactions. The only thing we're going to do is calculate oxidation number. Okay, call it ON, and the ON stands for oxidation number. All right, this is confusing, but so let's go back to the example of Husong and myself, VJ. Okay, a reducing agent is the substance that gets oxidized. Go back, excuse me, go back to us as a couple, as a redox couple. Here, I am the reducing agent. Why? Because I caused my partner's reduction. So I am a reducing agent. Okay, you see that? How it's kind of tricky? So I am the reducing agent. I get oxidized, but who do I reduce? I am the agent that causes, your reduction. So I am the reducing agent. Okay, on the flip side, what is Husong? Okay, he is the agent that causes my oxidation. That is, he gets reduced, but when he gets reduced, what does he do to me? He oxidizes me. Okay, so the definitions are, you know what I mean? Kind of backward. So, he gets reduced. He is the agent that causes his partner, my oxidation. So he is the oxidizing agent. Okay. So there's the reducing agent, and then there's the oxidizing agent. Once again, reducing agent. I am the agent that causes his reduction, so I am the reducing agent. On the flip side, he is the agent that causes my oxidation. Husung is a oxidizing agent because he causes my oxidation. He himself gets reduced. So that's the definition. By the way, how many electrons are being transferred between me and Husung? How many electron transfer reaction is this? This is a 1 electron transfer reaction. 1 electron transfer reaction. There'll be some that are 2 electron transfer, 3 electron transfer, so on and so forth. Okay, so again, just like with acid-base chemistry, this is the only depth I want to go into. For the exam, we want to calculate oxidation number. Okay, with this oxidation number, we can move forward. Okay, but we can't move forward unless we know how to calculate this oxidation number. So there are 6 rules. Okay, 6 rules to calculate the oxidation number. All right. Okay, so make sure you know these rules. Okay, so this can be tricky, so kind of bear with me here. Okay, rule number 1. Okay, rule number 1 is that free elements have an oxidation number of 0. Okay, elements by themselves have an oxidation number ON of 0. So what is oxidation number anyways? Okay, it's a number that we assign to an element to determine whether it gets oxidized or reduced. Okay, so it's just a number. If you read your textbook, they actually call it just a fictitious number. It has no bearing other than we want to balance a redox reaction. But this is a number that's assigned to an element to determine whether it will get reduced or oxidized. Yes, what you'll do is, which we will not do in this class, but you'll figure out the oxidation number on the reactant side, and then the oxidation number on the product side, and then you'll figure out the transaction, whether it got oxidized or reduced. That is correct. So we will assign a number according to these rules, 6 rules. The first rule is free elements, or elements by themselves, have an oxidation number of 0. Okay, so what does that mean? So what's the oxidation number of iron? Not iron plus 2, just plain old iron. Okay. Okay, it will be 0. Okay. You see it by itself, it's 0. Okay, what about calcium? 0. Okay, it's not bound to anything, so it's 0. Okay, what about O2? Even though, is the oxygen bound to anything, any other element? Zero. Okay. Okay, what about N2? Okay. Okay, if it's bound to any other element, then it will have an oxidation number. But if it's just by itself, N2, O2, iron, calcium, bless you. Okay, H2, what is the oxidation number of hydrogen in H2? Okay, so it's bound to itself. Okay, so if it's by itself, it's going to be 0. Okay, 0. The oxidation number for that will be 0. All right. Right, so what's the oxidation number of iron plus 2? Now that's when you say it's plus 2. Okay, now that's when you say it's plus 2. Okay, but if you see this just by itself, okay, it's 0. Yes. All right, rule 2 here. Okay, rule 2. Group 1 elements have an oxidation number of plus 1, like the ion, and group 2 elements have an oxidation number of plus 2, like the ion. Okay, like it's an ion. All right, so what is the oxidation number of sodium ion? It's the same as the charge, so it's going to be plus 1. What about calcium ion? Okay, it's the same as if it were to form an ionic compound, okay? You don't get confused with Na plus and Na. What's the oxidation number of straight Na? Or the oxidation number of straight calcium, no charge? 0. Okay. Right, what's the oxidation number of sodium in NaCl, sodium chloride? What does sodium chloride consist of? So in order for sodium to form sodium chloride, what would its oxidation number be? The same as its charge if it were to form an ion. And what about chlorine? -1, the same if it were to be an ion. Just get this out of the way. Okay. But if it was just sodium by itself, without the chlorine, without anything, it would be 0. All right, so I'll make number 3 and number 4 easy, okay? For me, in this class, we'll just make hydrogen as an oxidation number of +1, okay? So the rule is hydrogen has an oxidation number of +1 when it's bound to a nonmetal. When that hydrogen is bound to a metal, it's -1, okay? But I will just give you for the test hydrogen being +1. But I'll give you both, but on the exam you'll only see it as +1. Has oxidation number of +1. When bound to nonmetal. Okay, so this is something that, I will have you know for the test. Okay, for those that are interested in the more finer nuances, I will tell you that hydrogen has an oxidation number of -1 when it's bound to a metal. But this is the one I'd like for you to know, but okay. Right there. Okay. So what's the oxidation number of hydrogen in hydrochloric acid? +1. Okay, what's the oxidation number of chlorine to form hydrochloric acid?
Negative.
Okay, it will be the same as the ion, -1. Okay, what time do we have? 15? 20? Okay. All right, we will do up to page. We'll do this page and then we'll call it a day. All right, so we got 3 rules. Okay, let's do rules 4, 5, and 6. We'll do this problem, and then we'll see where we'll go from there. Okay, rule 4, just like rule 3, okay, where hydrogen is going to be +1. Okay. Oxygen is going to be -2, except for some rarities, but oxygen will be -2. Okay, of -2. Okay, oxygen will have an oxidation number of -2. So there is some instances where it will be -1, but we will not go into that. So this will be 99% of the time. Okay, so oxygen I want you to associate with -2. Okay, when it's bound to an element. Okay. When bound to something else. So that's what we're concerned. We're not concerned about the rare cases where it's not -2. Just know oxygen would be -2. So what would be the oxidation number of oxygen in H2O? -2. Okay, so the oxygen oxidation number would be -2. Okay, what about the hydrogen? It will be +1 from the previous rule, yes. Yeah, but for each one it would be +1. So this is how it will be, okay? So 2H plus oxygen is going to be 0 because there's no charge. And oxygen will be -2, 2H, H is +1, so 2 times +1 minus 2 is equal to 0. Okay. Okay, so we have two hydrogens. Each one is at +1. So +2 -2 for oxygen's oxidation number equals 0. The whole thing has a 0 charge. All right, the last two rules. Okay, rule 5. Fluorine will be always -1. Okay, the oxidation number of fluorine, the element F, okay, will have an oxidation number of -1. Okay, -1. So what's the oxidation number of fluorine in hydrofluoric acid? Okay, it's the same as the ion. What's the oxidation number of hydrogen in forming hydrofluoric acid? It's the same as the ion. Okay, same as the ion. What's the oxidation number of fluorine in F2? Is it -1? Fluorine by itself? Does that mean 0?
Yeah.
You're right. Okay, 0. All right, so fluorine will always be -1. You actually see that here. I know it's hard to see, but fluorine is just at -1. Okay, it's hard to see, I know, but fluorine has just one oxidation state, and that's -1. Now, all these others have all these different oxidation numbers. All right, the last one, rule 6, is that the sum of oxidation numbers must equal to the sum of the overall sum of the ion, or okay, the sum of the oxidation numbers. Okay, the sum of the oxidation numbers must equal to the overall sum of the ion or molecule. So what does this mean? Okay, so phosphate. Okay, if you remember from your flashcards, phosphate has an overall charge of -3. Okay, so this rule 6 means this. Okay, P plus how many oxygens? How many?
4.
Okay, equals what's the total charge? -3. Okay, -3. Okay, so the sum of the oxidation numbers must equal to the overall charge of the entity. Okay, of this phosphorus and oxygen, we know oxygen 99% of the time will be -2. Okay, so that whole thing must equal to -3. So P minus 8 is equal to -3. Here, P has an oxidation number of +5. And oxygen 99% of the time will have an oxidation number of -2. Okay, that's just one of the rules. So that's what it means. It has to equal to the sum of the overall charge. If the charge is 0, it has to equal 0. If the charge is -3, it has to equal -3. Okay. How about this one here, MnO4 minus? Okay, what are the charge of the oxygens? What are the oxidation numbers of the oxygens and the manganese in MnO4 minus? Okay, so you're going to do Mn plus 4 oxygens is equal to -1. Okay, what is the oxygen oxidation state? -2. And then here we'll just solve for the transition metal manganese. So here Mn is going to be plus 7, and oxygen is going to be minus 2. So the sum, okay, just like water. Okay, remember this one, Gerardo? We did this as a class together. 2H plus oxygen is equal to what? 0, because there's no charge. Okay, so hydrogen is going to be plus 1, oxygen is minus 2. You notice all the oxidation numbers add up to 0 because the whole water molecule is 0. All right, let's do these problems and then we will end the class. We just have 2 more pages, but we'll do those 2 pages and wrap up the lecture, or the chapter, next Tuesday. Okay, what time do we have? 10? Okay, got 10 minutes. All right, CS2O. Okay, so that is 2CS plus O is equal to what charge? What's the total charge on this thing? 0. Okay, 0. All right, so 2CS. What is oxygen?
Minus 2.
Okay, so what will CS be? Cesium? Okay, it will be the same as the ion, which is plus 1. So solving this for 0, you get cesium with an oxidation number of plus 1, and oxygen with an oxidation number of minus 2. So that's, oxygen minus 2, just know that. Okay. All right, what's the oxidation number of calcium and iodide in CaI2? Okay, calcium plus 2I is equal to what number? Okay, 0. Okay, calcium is in what group of the periodic table? So what charge is the second group? So it's the same as the charge for group 2. And so calcium is going to have an oxidation number of plus 2, and iodine will have an oxidation number of, what is that what is iodine equal to? Minus 1, same as the ion. Okay, same as the ion. Okay. All right, SbF6 minus. Okay, SbF6 minus. So Sb plus 6F is equal to what charge? Okay, here it's negative 1 because the overall charge is negative 1. So fluorine is going to be minus 1 always. Okay, that's just one of our rules. Sb is a transition metal, so it can take on all different oxidation states and have all different types of oxidation numbers. So Sb minus 6 equals minus 1 here. I'm getting Sb to have an oxidation number of plus 5. Fluorine will always be minus 1. Okay. Right, Fe3O4. So this one is weird because you actually get a fraction. Okay. Iron is very strange in terms of its oxidation rules. But here it's going to be 3Fe plus 4 oxygen equals to what charge? 0. Okay. So oxygen will always, at least 99% of the time, have an oxidation number of minus 2. So solving for that, we get iron with an oxidation number of 8/3, and then oxygen will always be minus 2. Okay, in fact, that's something you just memorize. Okay? Oxygen minus 2, hydrogen plus 1. All right, these last 3, let's see the different states of nitrogen. NO, this is nitrogen monoxide. NO2, this is nitrogen dioxide. And then nitrate. Okay, NO3 minus. Okay. In all of these, what will oxygen be? Okay, but take a look and see all the different oxidation numbers nitrogen can take in doing an oxidation reduction reaction. So it can be oxidized, it can be reduced. Okay, we'll first do NO. Okay, N plus O is equal to 0. Oxygen is going to be minus 2. So oxygen will have an oxidation number of plus 2, and then oxygen, as we always mentioned before, minus 2. Okay. So oxygen will have a plus 2 oxidation number here. Okay. Very strange. NO2 minus. Okay, what do you think the nitrogen oxidation number will be in order to form nitrogen dioxide? Okay, so N plus 2O is equal to what's the total charge? Okay, oxygen, as we mentioned, will always be -2 in this class. Okay, -2, but we have 2 of those. So here, oxygen will have an oxidation number of plus 4. Okay. So in forming nitrogen monoxide, it will take a plus 2 oxidation number. NO2, it will take a plus 4 oxidation number. And then finally, what will it take in nitrate? Okay, our last one. A lot of different oxidation numbers for nitrogen. Okay. N plus 3O is equal to what number? It's not 0. You all agree it's -1? N plus 3 times minus 2 is -1. And here, nitrogen will have an oxidation number of plus 5. Okay. Okay, so check this out. Nitrogen can be plus 2 oxidation state when it forms NO, a plus 4 oxidation state when it forms NO2, a plus 5 oxidation state when it forms nitrate NO3 minus. Okay, so it can get oxidized and reduced based on this number, plus 4, plus 2, or plus 5.